There's a baseboard and SOM. It's really, we would call it a single board computer, but it's a two boards because it's based off of an NXP reference design. So other than the outer components that had to be pre-placed and these critical connectors and mounting holes, really everything else on this was auto-placed, and it sure doesn't look like a human did it. And there were just maybe 3 or 4 instances on there where I took what Quilter generated and moved a couple of things.
Welcome, Sergiy and Ben, for another edition of Trace Talks. Thank you for coming back. So you were here like roughly a year ago, and a lot's happened in the year for you guys and for Sierra too. So I'm really anxious to dive in and understand more about that year and unpacking it. So that's exciting. Sergiy, let's start with you. Tell us about this big, audacious, hairy goal that you had for your company in 2025, and tell us why you chose that as the project and what was your intention. And start with why the name is the name.
Yeah, of course, of course. So thank you again for having us.
Of course.
It's great to be back. For those who don't know, at Quilter we're focused on the layout portion of PCB design, right? And trying to accelerate it and compress it as much as possible. And as a young company trying to make progress in a very technically difficult field, it's really helpful to set audacious goals that inspire the team and get everybody pushing in the same direction, right? Aligned in the same direction. So we wanted to pick a really tough design that people wouldn't initially think that software could help you largely automate, even in 2025. And something that would be simple for people to understand and explain. And so the simple statement of how the project started was, can we build a computer, largely with AI and with automation? And that was kind of the genesis of Project Speedrun. So we picked a quad-core processor, DDR4 memory, basically something that can run Linux, play video games, have a web browser, take a video call, and said, let's make that.
Something fun.
Something fun. Yeah. Something hard and fun. That's the big challenge that we took on in 2025, and we'll talk about this a bunch, but this is the board the 2 boards that we ended up with. And it was called Speedrun, frankly, as a team vote on the best name, but it's an apt name in that the purpose of this was about going fast, right? How quickly can we design that from beginning to end, in terms of layout, of course. And we got that down to just about a week of time, which is quite a lot faster than what is typical for a board of that complexity.
Okay, so how complex do you think this board is, let's say on a scale of 1 to 10? 10 being... And I'll let you even define, what is a 10 to you? And then where does that Speedrun fall on that?
I think there's actually 2 ways to define the complexity in terms of the distribution, right? So if you look at just technical complexity, right? With the 10 being the hardest, most technical board I can think of might be something like a data center accelerator card with a bunch of GPUs, or maybe like a phased array antenna for a satellite. If that's a 10, right, on a technical spectrum, this is probably a 3 or a 4, in my opinion. But what's interesting to me and why we were so adamant about pursuing this is that if you look at the distribution of how many boards fall closer to where this board is versus a phased array antenna or a data center card, I actually think it captures maybe half or more of the designs that are being done out there, period. And so I think it's far from approaching the most complex boards out there, by no means, but it is representative in the kinds of boards that real professional designers work on.
Got it. Wow, okay. And I like the way you're describing the distribution. You're at the stage where you're addressing, you would say, 50% of the professional designs out there?
Yeah, potentially.
Okay.
I think it's early to say that like in 50% of boards we can help in all cases. There's lots of nuances. This board was specifically a high-speed digital board, not a power board, not a high-voltage board. Lots of nuances we can talk about. But in terms of just raw complexity of like how many components, how many pins, dealing with the BGA, dealing with impedance matching, there's professional designers, well, not PCB designers, but like electrical engineers who maybe haven't even touched the board of this complexity before.
So right now, where your company is today, how do you see it making an impact to a professional electrical engineer who's working on something of that complexity?
Yeah, the number one thing we focus on, what this project was meant to demonstrate, and also what we work on with customers, is speed, right? That is the number one outcome that we currently aim for.
Not functionality?
The functionality still has to be there, right? So for example, like I had a customer tell me about, overwhelming demand for boards, overwhelming demand for designs. They have potentially a 6-month queue for a designer's time. And so, if they test parts, they can't get a board for that long just because of a shortage of skilled labor to do these designs. But they're very proud of their success rate, right? That like more than 90% of the boards that work don't need a respin. And that's incredible and amazing. They cannot tolerate a loss in that, very understandably. But 6 months is a long time, right? And we got to bring that down. And so at this point, Quilter is not aiming to help you increase that 90% to 95 or 98. What it's helping you do is compress the time that it takes to make a board, and therefore help you get through your queue of all the different test boards and R&D boards that you've got on your plate.
So right now you don't think Quilter is better per se, but it's faster.
Correct.
Is that where you are?
Yeah, I think that the way that you can arrive at a better design as a designer using Quilter is not that Quilter is going to tell you something you don't know. It's that in the same time you would have done one iteration of a board, you might do 3. And every engineer that we talk to, when we ask them, like, what would you do with more time? If you can do more boards and you can do them more quickly, almost unanimously, the answer that we get is test more, right? Get more confidence on the schematic, get more confidence on the characteristics of the board, get more confidence on the edge cases. And so you might arrive at a better design using Quilter, but not because Quilter told you something you don't know about board design, but because you got to do 2 or 3 iterations in the time you would have taken to do one.
Okay. That sounds good. Ben, can I jump to you?
Well, I want to add to that too. That's absolutely 100%. It gives you more that you can play with.
Well,
Now, I have and part of that is there are things now in Quilter because of this project and what we had to build and how we had to train our models throughout the year to get this to be successful, which exploratory in nature. So automated component placement is kind of a big deal. There have been many attempts at algorithmic auto places over the years. Most of them never, they end up on the trash heap. Professional designers are reluctant to use them more than once to see what random weirdness results. And I saw that many times as an EDA veteran that, what's this auto placer thing? Oh, okay. Clearly that doesn't work. And I'm very proud of the work that the Quilter engineering team on the software side has developed over the year in this project, because the placer alone will help people unlock ideas and solutions that perhaps they hadn't tried or thought of, and allows them to iterate on those things as well.
Oh, interesting.
Yeah.
That's a great point. So then let's dive a little bit into that. So what were the challenges that the software team, and of course you can answer as well, like what were the challenges the software team had to overcome in, this auto placement? Why is this better and not what exists as good?
I can't speak to the internal workings and big mathematical problems they solved. I can say I know those guys, and they are utter geniuses, like everyone who Sergiy seems to know and be able to pull into the company. But from a user perspective, as the electrical engineer on this project, I saw really fabulous changes in like intelligent grouping of components, the ability to drive a floor plan, the ability to have Quilter router board that was human placed and do a very good job, but also have it place all the popcorn and other components. So for example, on this board, apart from all the connectors that had to be specifically placed for the SOM and
Can you show us?
around the edge of the board, there's a baseboard in SOM. It's really, we would call it a single board computer, but it's two boards because it's based off of an NXP reference design. So other than the outer components that had to be pre-placed and these critical connectors and mounting holes, really everything else on this was auto-placed, and it sure doesn't look like a human did it. and there were just maybe 3 or 4 instances on there where I took what Quilter generated and moved a couple of things. But throughout the course of that time, our Placer team had built support for understanding, and not just the Placer team, it's really the whole company was involved, but we have what's called circuit comprehension. It's basically a way of the engine examining the input files, the PCB and the schematics, and just being able to start to intuitively identify different groups of circuitry and different types of things. So for example, on that baseboard, there are DC to DC converters, and the switching regulator chip and the big inductor and the bulk capacitors, they're all grouped together. And that was done automatically by our Placer, which is based on reinforcement learning. So like that kind of seeing the advance throughout the year to what we were able to do with this was very impressive to me. And it just highlights that as a designer, it's going to allow me to explore more solution spaces. So that's just one example. Bypass caps is another. There's several things in there. And on the routing side, we went from just releasing diff pairs, probably the last time that we spoke and we're on the podcast, we had just announced support for diff pairs.
Nice.
To being not just diff pairs, but some length tuning capabilities were added and used on this SOM board, as well as impedance control.
So like that's amazing. It sounds fantastic. I like what you're saying about, it seems to me that it's still a companion to the human, and so there's human in the loop still.
Yeah, currently, and that's intentional.
Yeah.
At the end of the day, it costs time and money to get boards made too, which we worked with Sierra to do that. When we were satisfied with our design candidates. At the end of the day, we as the ultimate user or customer or engineer, there's high stakes riding on getting boards manufactured and assembled. And so, it behooves us to have that final responsibility of making sure we're satisfied with the result. It's no different in the general AI and developer community that, I'm listening to a lot these days. We're not yet at that stage where you could just hand everything off to an agent and trust it. That's dangerous, and no one in their right mind would do that. I mean, we might eventually get to that stage. But I hope we do, because my life's too busy to not have agents helping me.
Okay, good. So now from a software perspective, how would you answer that different? Why is, your placement algorithms, let's say, any different from what exists in the market today?
I think Ben nailed the most important pieces of that, right? Like, if you're going to do a good job placing, it's not about coming up with some algorithm that has some heuristic for clustering or something. Like, you have to respect the physics, is really the best way I can put it. Like, the way that we look at this problem is that, for a board of this complexity to work, there's, 10,000, 100,000 constraints that must be true. And if any of them are not true, then there's some chance the board doesn't work, right? If that switching converter is placed in a really poor way and you've got a long return loop, it's going to ring, it's going to brown out, it's going to be unstable. That's not a working board. And so to go through and identify all this is quite laborious. And then it's a separate problem to make software that then looks at those constraints and says, can I find a solution that meets all or most of them? Right. And so we really break up our efforts into those two things. And the electrical engineering guidance is, what are the questions we must answer rigorously, quantitatively, not intuitively, about the constraints we have to meet for which components to be placed close, how they need to be routed. We also, for example, developed power polygons to support, a good power distribution network on this board. So the electrical engineering know-how from people like Ben tells us what those constraints need to be, and then what the researchers and software engineers in our team do is work on algorithms that find a way to satisfy all those constraints. And a project like Speedrun is really just a forcing function that forces you to say, like, for this board, here's everything you have to do, and it included things like length matching and power and floor planning and crystals and switching converters and so on and so forth.
No, I think that's really amazing. I think that it's always good as the CEO to push the company and have a guiding North Star and, then make it so that, hey, you're here today, but you want to be there tomorrow. And so figure it out. I've hired a bunch of smart people and, with a certain amount of direction, they need to figure out the problem. So let's unpack that. Assume I'm a complete layman, which I am. What constraints did you give the software engineers for this board?
Well, and it's not even so much as giving it to the software engineers, although we had many meetings discussing board fabrication and assembly and design so they could understand the problems that we're building to solve. But it's Quilter that I give the constraints to. And to a large extent, it is already, as I mentioned before, we have circuit comprehension. It's already detecting certain patterns in the files that I've uploaded to it with schematic and PCB. And then it gives me basically a table or kind of like a spreadsheet view or constraint view before pressing go on the job. And it allows me to edit those. I can even upload CSV files. So as input to this design, I validated what it had detected and made some tweaks to things like this is a switching regulator and this is the inductor associated with it. This is the bulk storage cap associated with it. This is the input bulk storage cap associated with it. Cap being capacitor, of course. So these are components that have to be placed together and close and will have thicker, higher current traces. So that's another one, is for all of the power nets, specifying what the minimum, or really in this case, I would have said the maximum current handling capacity that's needed on that net. And then Quilter is able to make a judgment as to how thick the traces are. Or in our case, we'd just released that automatic polygon generation thing, which I've never seen in any ECAD tool ever until now. This is very innovative. And it actually made polygon pours for some of the power nets and things. And I did edit those by hand in my cleanup pass. But out of the box, it did a great job.
So how does it know that it should do some polygon pours and where to do them?
Well, again, it goes into that circuit comprehension, the constraints I'm telling it. So when I define the power nets, I can check a box that says make pours or attempt to make polygon pours. So it's basically telling Quilter, you don't have to route this with a really thick trace. If you want, you can just make a polygon for this net. And so I make sure all the power nets are in there. There's the impedance control nets. This board uses DDR4, so there was the definition of length tuning requirements and impedance requirements for those high-speed signal nets. Same for MIPI, CSI, and DSI. So this board has a camera interface and a video output interface that goes to a little module that gives us HDMI for a display. All of that's like high-speed diff pairs. There's PCIe bus, a single-lane PCIe that's PCIe Gen 3 compliant. So it has a 100 megahertz reference clock. It needs 85 ohm diff pairs. So the impedance and requirements of all of that is added in up front.
Need to calculate impedances, choose materials, and run DFM and bump checks? Sierra Circuits has like a zillion PCB design tools. That's way more calculators than layers in your stackup. Check them out at protoexpress.com/tools and give our engineers a break when you send your files with fewer errors.
And then,
So how did you add the impedance requirements? Did you just drop in some note of some sort, or do you text it, type it in free form
When
text?
when we started this, I had to manually enter things into tables on the UI. A lot of stuff, it was automatically detected in there, and I just had to set the right numbers, like what impedance I wanted. As of today, and right around the time, or just before we went to production with this, we had the ability added to just download these circuit comprehension constraints as CSV files, so you can even edit them in Google Sheets or Excel, and everything's tabulated. So it's very easy to get a lot of information into the system up front.
Did you make that open source, the constraints that you gave to the system?
Yeah, the constraints I put in, or that we put in for these prototypes, I think ultimately we worked on a few iterations, and I think the SOM board, Sergiy, you actually kicked off the job for that one. But yes, these are available, and there's links on our website, and people can see what the constraints were for the jobs if they need to.
Great. So I understand it took about a week to route this, if I'm not mistaken, or end to end. Give me a detail of the timeline.
The routing, the part that Quilter did was actually way faster than that. The baseboard run in AI was 27 hours. I think the SOM was 15 because it didn't have to do any placement. So the placer part of our software it bypassed that because it was pre-placed by human in this case. But that's the actual time it took to get results that were good enough that we picked them and said, we're going to build that one, so let's get that and download it and start cleanup. Then I personally spent, I wouldn't say it was less than a week, but it was about a week, 60 hours on both doing tidy up. Now, a lot of that tidy up too is because, I needed to adjust a lot of the silkscreen text or remove them or do things like that, we haven't really solved for those things just yet. We're still working on that stuff. That's sort of more like the icing on the cake, let's say.
Sure.
And so, in all, and this design to do the component placement and the board layout I won't say from scratch, but at the starting point of what we submitted into Quilter to do the placement and routing, the same amount of time we had some very seasoned contract board layout specialists quote us and give us objective numbers about how long it would take them. And we paid them for that so that they were unbiased. And
did they actually lay out, or they just gave an estimate?
No, but these are people who've done thousands of boards.
So they know.
So they're accurate.
Okay.
And one very seasoned expert in his CAD tools, let's say, not dropping any particular ECAD brand, came back with 400 hours or 450 hours or something. I've forgotten the numbers now.
I forget the exact numbers, but
the other was one was like 460 and the other was like 380 or something. Yeah. But they were on par.
10 to 20x from what it took Quilter to do, roughly.
Yeah, roughly 10.
Wouldn't it be interesting to actually, get someone to submit Quilter to like a layout competition and see what kind of shock and awe might come from that?
That does sound kind of fun.
Yeah. So are those all the steps in the development? So placement, route, cleanup. What else is left after that?
That's pretty much it. I think it's good for people to spend whatever time they need to be really clear with their schematics up front. And, the starting point for Quilter is a board where you have the outline you have critical components already placed. Anything that you are happy for Quilter to place is left off to the side. And you can give just the board to Quilter, but it will do a better job of that upfront detection of circuit patterns, circuit comprehension, if you also give it the schematic files. Because Quilter will look at things like this capacitor is on a power net and it's directly wired in schematic to this component pin, so it's probably the bypass capacitor for that pin. And it's actually very accurate with a lot of those things. And so that saves a lot of time in the setup as well.
Let me give a little color to this from like the kind of customer perspective, right?
Sure.
Like, I mean, Ben and I are frankly experts in Quilter. We have to be, right? But when we work with a customer for the first time, that's obviously not the case, right? Like they don't know the tool, they don't know what to expect, how to set it up. So they're not likely with the same board to get a 10x speed up right out of the gate, right? I mean, for one, it's this specific type of board, right, that we kind of went after, that we nailed, that doesn't necessarily transfer to all boards. And for two, like, there's expertise we have in just like the quirks of the system, what it does well, what it doesn't do well, exactly how much guidance it needs, right? So when we work with a customer for the first time, like in a more fair evaluation of like, hey, I've never seen this before, let me sit down and take it for a spin. There you get a lot more, and we frankly coach and help customers with a lot more iteration. Right, so somebody throwing in something into Quilter for the first time is actually not going to get a good result, right? Because if you haven't told it what the constraints are, it's not going to meet any constraints, and it's not magic, right? Like we say this over and over and over with customers. There's no magic. It's everything that it's going to do. It's going to show you, and you're in control. So then we'll teach like, hey, like it's helpful for you to still control the floor plan, and they'll learn that like using Ultium rooms, for example, like to specify where the different sub circuits should be and how they should flow. That helps a lot. Spending time in the circuit comprehension section helps a lot. But even then, like in the case of modifying placement, we'll encourage customers to look at the final routing output, judge it, and then say, oh, you know what? It would be helpful if I tweaked a few components and a few placements here and there. Download the placed only version, make the changes, resubmit. Now that your placement is fixed, you've reviewed it, you're happy with it, focus on the routing. You see what it does well in routing, what it doesn't do well in routing, delete it, fix the parts that you think need to be done in a very special way, right? If you have some like RF lines or something like that that need a lot of care, lock those in, resubmit. And typically like a successful customer on their first or second try probably goes through about 3 or 4 iterations like this to get a design that they're like happy to manufacture. And of course that goes down with time and with experience, but at the end of the day, it's not magic, and it's not going to just do this thing for you. It is some push and pull between like the human and the machine, and the combined iteration is much faster than doing it manually. But it's not all just like throw it in, magic comes out, and it's done. We're not there.
So no, magic is good. It's a good thing to try and attain. But so how many iterations then on this, like in terms of like getting your constraints right? And
I mean,
it took you all year essentially, right?
Exactly. Like the iterations in this were really on the software team.
On the software team, right.
Like so, like Ben knows, hey, we need length matching on this. Well, it's going to take a long time for a team to figure out how to length match on a board. Like that's a hard problem. And so we ran nightly builds of like, hey, like how did it go? Get Ben's feedback. What he says needs to be codified into actual quantified constraints that then the code can check for itself, and so on and so on and so on and so forth. So, but it was less about iterations on the board and like what the constraints should be, and more iterations on the software that can make the board.
Right. So, devil's advocate, why is Quilter's impedance feature set any better or different from another EDA tool's feature set for routing impedance traces? Yeah.
So there's no difference in terms of like how you shape your transmission line to match that impedance. Like in fact, like we actually don't want to do the impedance field solver ourselves. We'd much rather take a trusted EDA tool and have it calculate or let the user specify it. What Quilter will do is, as it routes, it'll make sure that that impedance is respected, right? And then if it knows it's a critical trace, it'll kind of keep things away from it. And then at the end, when you're done with the routing job, it'll give you some report of like, whether the differential pair was still coupled and what fraction of the length was uncoupled, and so on and so forth. So it's not so much that we've like we have not made a field solver that we're claiming is any better at matching the right impedance in terms of cross-section. We just can factor that in during the routing to make sure that it's respected as you route the actual transmission line.
Got it. Okay. Do you have a same answer? Different answer?
That's
Pretty
a
much the same.
perfectly succinct answer.
Okay.
At the end of the day, these are very well understood problems by humans.
Yeah.
Like people have been routing impedance control boards for a long time.
Right.
So we know how to do it. It's just a matter of, it's really table stakes. If we're claiming that this automation has this capability, we got to build it in there.
That's
it's
right.
table stakes.
Right.
And then going back to that input and that whole process and being able to iterate even just with placements before you let it fully go out and route the board. It's really analogous to the way the most effective users of AI in the software industry today work. They don't just go and tell whatever their preferred large language model is a prompt to say, build me this new software program that does this and that, and it's called this, and it has all these features, and it'll go and make me millions of dollars. Those prompts get nowhere. Instead, the name of the game is you have a conversation with it and you iterate. And that's absolutely a strength of these kinds of automation tools.
So that's good. I think that makes a lot of sense. And just curious, how much would one of these iterations cost? I heard, tens of hours for a design. Do you have an idea of the cost it would, for the user?
Yeah, I mean, there's a difference between what we charge and like compute costs, right?
Yeah.
And the compute costs are orders of magnitude less than labor. So, rounds to, I mean, it's not zero, but it rounds to zero in the scope of like what it would cost a human to do this task. But the way that we kind of price is to be at cost to labor, right? So what we actually do with the customers, we'll say, we'll charge you on the upload. Right? But then you get as many iterations as you want for the span of like a couple of months. And the benefit of that is that for one, the customer's not afraid to like play with the design and try it as 4 layers, try it as 6 layers, try it this way and that way. But also if they have a schematic change that's late breaking, right? If inevitably there's some part that's out of stock and they need to redesign, that's all okay. Like that's a part of your one design. So they end up paying at cost to labor. They get a significant time compression, and they get a lot more iterations than they otherwise would have, and ability to handle late-breaking changes, which inevitably always happen in a project like this. And it takes them all the way through to the point of submitting to Fab.
Okay, let's talk about submitting to Fab. So what was that process like?
Yeah, so I mentioned earlier there was a week of cleanup on me, making sure I was satisfied with all the polygons and everything, and getting it ready. We were working with Sierra on prototyping these. We also did that because, we knew it's a domestic or same time zone even Fab that we can travel to if we have to, if there's an issue or anything like that. We also knew the advanced capabilities. So really, it was a matter of doing our own design rule checking. These boards actually, I did my cleanup and output generation in Altium because that's the tool I'm most familiar with, and it's the most. At the time, it was the most supported tool with Quilter, although we support Siemens and Cadence now, and as well as KiCad, of course, and. So that process was really about generating a clean ODB++ data set, which normally is enough for full production because it includes the component bill of materials, it includes all of the images needed for actual fabrication of the bare boards, it includes the layer stack. Because we knew we were working with Sierra, and this board was originally derived from a semiconductor manufacturer's reference design. There were some leftover fabrication notes which I was not diligent enough, to be honest. And this is not an area where Quilter has any automation involved yet. but I had to put together and edit the fab notes as best I could. I also worked with the Quilter engineering team up front and gave an early submission for quote. And that was an extremely informative process. There was a bit of back and forth, but it was very helpful because it highlighted to me that we have requested a layer stack with materials that maybe aren't in the US supply chain. And so, we had to find alternatives that were still going to allow us to build the board and maintain impedance and be equivalent. And so we went with Ventec VT47 in the end for the SOM. I think the baseboard was less critical. There are some high-speed nets, of course, like PCIe and whatnot, the MIPI interfaces on the baseboard. So it's still important to have those impedance controlled things controlled. But in that process, we went back and forth and were able to establish exactly the layer stack for each board. It also highlighted to me, just on that subject of layer stacks, it's really important that designers and engineers who do board layout really need to know this. If I design the layer stack according to what materials Ventec, say, have on their data sheets that I download from their website, based on the information from Sierra, I can add all of those to my material library and design a beautiful layer stack in Altium or whatever tool I happen to be using. But all the data I have is from their data sheets. It doesn't factor in the squeeze out of material during lamination, for example. And there's no way to really know that up front. Those are things that only the fab knows. So it's really important to establish early, before submitting to fab, establish if anything's going to change significantly with regards to thicknesses of materials and things like that.
Absolutely true.
Yeah, so that was the process, and most of the initial problems I had were actually supply chain related. Surprise, surprise. There were the USB Type-C connectors, the audio output jack, the power on-off switch, and the push-button switches for reset, and, soft on-off, and an IRDA interface. I couldn't get any of those. And there were quite a few other smaller popcorny components like inductors and caps and things where it was helpful having Sierra's additional set of eyes over those on the bill of materials before assembly to consolidate all the things that we were actually going to assemble onto the board. So I had to go back after we had our result and after cleanup and redo 4 or 5 footprints on the main board, on the baseboard. Fortunately, the SOM didn't require any of those changes.
Yeah, feedback is what we do. we give feedback incessantly to designers, and they could be early on designers, a couple of years of experience, an EE trying to lay out something for the first time, or even someone who has 20 years of layout experience. Design's a big elephant, and there's always chances of a mistake. So having a second pair of eyes is great, especially a manufacturer who has to make it.
That's right. And we, frankly, we scrutinized Sierra's capabilities page and documentation to enable us to get to the level of completion that we wanted to. And that actually meant going down to two, maybe it was 2.5 mil trace and space on the SOM module, but it's an 8-layer board, and I foolishly asked for 5.9 mil via holes, which is the smallest mechanical drill bit that's typically available. And that was another thing where I got feedback. It's like, yeah, we could do that, but you might have too much breakout because of the via diameters and everything. And at this point, we had very dense routing in and around the DDR and the CPU. So I wasn't going to rework all of that by hand. I was able to basically agree with Sierra that we were going to do them as an HDI stack up and semi-additive process. So yes, that added some cost and time to the fabrication, but it was still, the point was it was still an accelerated design exploration. And every board, we had 10 boards manufactured, 10 base boards, 10 SOM boards. Every single one, bar the one that's in the bag over there, which I brought, were opened and plugged in and powered up and booted to Linux. All of them work.
That's amazing.
I'll take that one step further. I have a copy of one on my desk that's been running for 3 months straight now,
Nice.
without like Linux dropping out or rebooting or doing anything funky. So
Nice.
they're not just boot, like they were pretty thoroughly stress tested, and now at this point like a few months of uninterrupted runtime.
Yeah, we tested all the I/O,
Yeah.
the PCIe. I plugged in a M2 module for some other Ethernet thing, and I could probe it in Linux, and it gives me all the right information. So like we tested everything on this. So we were very elated when we plugged that
Oh, yeah.
first one in and it actually booted. We were
Oh, yeah.
like, wow, like that's just a moment to savor.
Absolutely. That's great. Every designer loves it when their board boots
Board
up.
works, yeah.
And the
For the
smoke
first
doesn't
time.
come out.
Yeah.
I've never seen smoke. Okay, great. Well, so when we get a design from any designer, we're combing through with our tools to check for, spacing violations primarily, any kind of solder mask violations, things like that. And we did find some on your board. So then how did you handle, were you able to handle any of the kind of modifications you had to make with Quilter, or did you have to manually modify when we gave feedback?
The feedback I did get was minor enough to just go and fix it on
Okay.
the board straight away
Okay,
and then resubmit.
okay,
So really that wasn't, it adds time to that cycle when those feedback points happen. But again, I would say a lot of that was on me for not being quite diligent enough with every single detail up front. So for example, one of the things that came back was, as I mentioned, I had to put some new footprints on the board for parts that I had to substitute. And one of those was a brand new right angle tactile switch from C&K, which is now a part of Littlefuse, I believe. And I looked at the data sheet and I built the footprint according to the data sheet, and to me, what they were calling for was offset slot holes for the mechanical mounts on the side of it. And the Sierra team flagged that as, we think this is a mistake. Oblong-shaped holes in oblong-shaped pads are very rarely offset to the pad shape. They should be aligned. And I told them, that was just one instance where I'm like, I went back and fixed the footprint for future revisions, but for this production run, I said, please ignore that, just go ahead and make it that way anyway. And fortunately, they came out, they assembled just fine, but it was a point of concern. And there were a couple instances like that, but they were, I would say, not like so significant I had to go and rerun the board through Quilter and get an alternative placement or anything like that.
got it.
Yeah.
Speaking of footprints, does Quilter address that in any way? No. Are you going to or plan on it?
No, the customers we typically serve tend to be larger companies that have
Okay.
like a well-fixed library, and it's carefully controlled and assembled, and they want us very much to just use the footprints they have. I think for smaller companies, certainly for like hobbyists, that would be nice. But I mean, as a startup, we must focus. like focus is absolutely critical. There's so many problems to solve here, right? Like as Ben already mentioned, we don't handle silk. We don't yet take special precautions in solder mask, right? Beyond just the basic, placement we're just doing mostly for the copper. So there's a lot of things for us to solve that I think are super critical already in this flow. And maybe one day we do footprints, maybe not. Maybe some other company already does it well, maybe not. But in the name of focus, we're assuming the footprints are done, and it's not typically one of the customer requests that we get.
RF designs driving you crazy? High-speed PCBs making you question your life choices? Relax, SierraConnect is coming to the rescue. We take care of the difficult stuff, and you can take the credit. Visit protoexpress.com and let's make your design the one everybody is reverse engineering.
So that makes perfect sense. I wanted to ask you, so what do you see are the big challenges right now? So you did your project, it was successful. Congratulations on that, that's fantastic. Always celebrate the small wins, it's important in life. Now, what do you see are the next big challenges, and what do you want to accomplish in 2026?
Yeah, for us, 26 is all about commercialization with customers as partners. Like 100%.
So you think the routing is ready, you're good to go?
I wouldn't say that. I wouldn't put it that way. I think that the way I would put it is that the core engine is strong enough to have a strong commercial purpose. To get to the phased array antennas and the data center cards out there, we have orders of magnitude to go. And like our team is going to be pushing on that and investing in like long-term research for that. But to get a useful product in customers' hands that accelerates them today on a good fraction of their boards, I think we have enough of a core solver. What it needs now is control and polish, right? So overwhelmingly, the kinds of requests that we get are about control, right? And especially as some of the larger companies that take DFM also into their own hands, right? In addition to relying on their manufacturers, they have a lot of internal built-up knowledge about, separations and tolerances and heating and so on and so forth. And for them to use Quilter in their production workflows, even in their development workflows, those have to be met. Right, like designers don't want to sacrifice the quality that they already designed to in the name of speed. They need to at least maintain the quality and gain speed. And we believe that our placement and routing engines are fundamentally capable of respecting those things. But there's an order of magnitude more constraints that we have to give it in order for the engine to actually respect them. And so we're trying to make it much easier to add constraints to Quilter, both in terms of how the user does it, but for us as software developers, of like how we express new constraints without rewriting the code.
You need to dive into that and just give an example.
Yeah, sure. I'll give a really simple one. On these boards, as far as the copper clearance, we had a single number. Right? So every net must be 3.5 mils on the baseboard. I think it was 2.5 on the SOM from each other, right?
Okay.
And so one clearance number. And that worked. But in the vast majority of cases of customers that we speak to, when you ask them for their clearance tables, it's a full table, right? Like your via to pad distance is different than via to via. And of course, if you have high voltage, that matters, and so on and so on and so forth. And so very plainly, every object might have a custom separation number to every other object. And that is probably the number one most requested feature that we're trying to serve now, is how does a customer maybe take it from their constraints manager, maybe state it manually, maybe take us a high-level requirement like, hey, I have 200 volts here, obviously you're going to need clearances. And then how does that distill into pin-to-pin separations, pin-to-via separations, net-to-net separations, so on and so forth. That's a flavor of the type of constraint that we have to deal with.
Got it. And so you're not building that into the code, you're extrapolating that out a little bit, the constraints? Because is it going to be different per customer?
So yes, it's for sure different per customer, and of course different per design, right? Like in some designs, designers generally feel most confident to leave as much margin as possible, understandably so. So if a design can be done with 6 mil trace in space or 8 mil trace in space, you should do that, even though the fab can do much smaller than that very confidently. And so, of course, you can choose it on design level and of course, company by company. So the core thing here is to distinguish, how does the customer state their constraints versus how does the software then respect those constraints. So on our side, on the solver engine, regardless of what constraints the customer gives us, as long as a human could find a solution to all of them, the software should aim to do the same. But which specific constraints apply to which board is in the customer's hands. And this will go in multiple ways. Like I think for simpler boards, it's very reasonable to go to Quilter and like pull up a net class, say, hey, this is a high voltage net class and here's my constraint. But for some of the other kind of bigger companies and customers that we work with, like they have well-defined standard practices for like, this is our constraints manager, these are our templates, these are our naming conventions, like the size of the via is in the naming convention, the type of current on a trace is in the naming convention. And for them, what we're probably gonna do is set up like custom templates where a company can say, hey, when you see these conventions in our CAD file and our constraints manager, that means this in like Quilter's constraint system, so that we can more easily kind of load them in from their standard process.
Okay, got it. Can you talk a little bit about the models that you're using to achieve these amazing results of speed?
Yeah. So I think the first thing I'll state is that like the most people I talk to will assume that this is based on like OpenAI ChatGPT or Claude or one of these language models. And the first point of clarification is that this is not a language problem, right? Like large language models, LLMs, are built for language problems, and this is fundamentally a geometry and physics problem. And so I don't think it's a suitable approach. And I think most of our viewers here, most electrical engineers have tried ChatGPT, asked it some EE questions, and had a nice giggle. So we can't use LLMs, right? That's one point of distinction, is that we have to build our own models that are meant specifically for 2D geometry, 3D kind of physics constraints, so on and so forth. The second thing that we do a little bit different than what people are used to from thinking about how ChatGPT works is that we have to treat this not as a supervised learning problem, but as a reinforcement learning problem. And to paint the distinction, when you train ChatGPT, what you're really saying is given this input text, a human would produce this output text. Please try to do that. And then you show it trillions and trillions of examples of this input text leads to this output text, and the model probabilistically tries to approximate that. Now, in PCB design, where are we going to get a billion designs that are all perfectly done and like every fab would be happy with? That doesn't exist. Right? That doesn't exist. So we have, and for what it's worth, even if it did exist, there's two fundamental flaws with taking that approach. Number one is it's still probabilistic. All models are probabilistic, but you can't be 99% certain you hit all the constraints. Like you have to nail everything, right? So hallucinations are unacceptable. The other problem is that good designers leave a lot of margin in a lot of places. And as companies push on really cutting edge products that like squeeze down on size, squeeze down on weight, squeeze down on cost, you want to cut out that margin and be really sharp, right? Like sharpen your pencils as much as you can. There's not a big data set of that either, right? And Quilter's aspiration is to eventually really sharpen our pencils and where necessary, be able to write right on the boundary of margin, right? But precisely and reliably. So the way to do this, in our opinion, is to frame this as a reinforcement learning problem, which consists of kind of three major pieces. In a reinforcement learning problem, this comes from the history of like playing games, right? Like playing chess, playing Go, playing poker. These are the kind of classic examples of where this field grew up. First, you have a game, right? So some sort of system where you can make moves and the state changes. So in our case, the game is kind of like opening a classic CAD system and like placing components, rotating, so on and so forth. And we've effectively developed our own CAD system, just it has no graphical user interface, right? It's meant for a machine, not for a human. The second piece is the reward, right? Do you win the game or do you lose the game, right? In chess, it's a checkmate. In Go, it's number of stones. In Quilter, it's have you met all of the physics constraints that must be met to be confident that this design will work once manufactured, right? That's winning. And then, of course, the third piece is there an agent that can play that game and get better and better at winning that game. And effectively, you run that in a loop. You let an agent play the game, you give it some score, and when it does better, you make it more likely to do that. When it does worse, you make it less likely to do that. And if you do that billions and billions and billions of times, you get surprising results where you get historically games like Go are now by far better with machines than with humans. Certainly chess has been that way for a while, and eventually, hopefully, even PCB design approaches that. So those are the two main differences, right? Not a language model, has to be a geometry and physics model, and not trained on imitating humans, but rather satisfying physics constraints.
And that's critical. I mean, at the end of the day, a working board that's manufacturable and, you know, in the future will be manufacturable cheaply, that works every time, is more important than having a board that looks pretty.
So what? Oh, sorry. Go ahead.
I think as these models and the reinforcement learning approach evolves and the model gets better and better, it's actually going to take on a beauty of its own, much like some of the other pattern generation things humans have been playing with have done for years.
Okay, great. So you mentioned PDN and doing your copper pours for better PDN. Like, what other kind of physics problems have you addressed, and what kind of physics constraints are in the back-end models?
Yeah, I mean, so to make it very explicit, when you come and use Quilter, everything is shown, right? So when you upload your board, we take you through the circuit comprehension process, and the purpose of that process is to understand effectively what exactly is the signal in every pin, right? And there's some subset of like critical signal types that we are capable of understanding, and we'll take you through those. And by omission, anything that's missing is not there, right? So as an example, we have a way to identify that you have a high current in some part of your subcircuit, but we don't have a way to identify as of today a high voltage. So the fact that you don't see a high voltage means that model isn't there, and it's not going to consider it. Now, you do that on the setup side, and then after Quilter runs, Quilter also gives you a design review, like a report of like, against all the constraints you gave us, precisely what did we check, and did we satisfy it, or did we miss it, right? And so for something like a high current, it'll be looking at, I mean, frankly, just the IPC formulas of like how thick does the copper need to be to reach no more than a certain temperature increase. For a differential pair, you want to do checks like making sure the impedance is right, the coupling length is good, that you don't go over a ground plane split, so on and so forth. And so effectively today, to keep all of the reinforcement learning fast and all the iterations fast, we reduce everything into geometry checks. Right, much like a PCB designer would. And then for high current, for switching converters, for crystals, for bypass caps, for power, and maybe one or two other things I'm forgetting, there's like 4 or 5 individual checks that are just distance, width, length, separation. They get listed out and verified.
It is essentially it's running a design rule check or a constraint rules DRC.
Makes sense. That part's not recreated or different in any way than from...
I would say the only difference is that like DRC in Altium or in Cadence or in Siemens is much more focused on typically nets, like clearances, widths, that sort of thing, neck down length, and I think mostly deriving from manufacturing, right? Mm-hmm. Manufacturing requirements. Yeah. Mm-hmm. But that's insufficient, right? Like you also need to consider the just electromagnetics requirements, right? So as an example, a high current constraint saying a trace has to be at least 20 mils, sure, that can be expressed in a classic DRC engine. But the fact that a switching converter needs to have a tight return loop and that the inductor needs to be close, the caps need to be close, that's not in the DRC engine, right? And so the innovation here is not so much that like we're doing some special physics that nobody has access to or anything like that, right? It's still just geometry. But we go further than to take the basic kind of manufacturing rules that are important, but we also take the circuit requirements from an electromagnetics perspective and convert that into geometry that is also important.
Got it. That's great. Any more of those hard problems to solve in 2026?
Oh, tons. Tons. Yeah, I mean, I think that improving the number of constraints we can handle and how reliably we handle them is the name of the game for 26. Like, my kind of core belief is that if you look at this board, it's as we discussed at the beginning, it is not the most complicated board on earth. but there are many designs that are of this order of magnitude of complexity, right? I mean, actually, we're sitting at a table with a bunch of sample boards.
Yeah.
I would venture a guess that these are roughly on par with this in terms of complexity, right? And so, like, as far as component count, pin count, we're in the ballpark. But as far as the reliability of all the types of constraints we meet and how reliably we meet them, that's where we got to get sharper in 26, right? That's what our customers are really asking us for. Of course, it'd be nice if we could solve a 50,000 pin board, right? But I think it's more important that we get really good at this scale of complexity first.
And in 2026 is all about constraints.
Yeah, reliability and constraints.
Reliability
100%.
and constraints. Yeah, that makes sense. So keeping your focus in terms of your roadmap is let's not tackle this uber complex boards.
Correct.
Let's keep it in the middle range, attack the wider market, but do it well and really get a reliable circuit board out of the design process.
Yeah, like the way I think about this is, as we sit down with prospects and customers as they evaluate Quilter, which that's a significant task, right? Like it's not something you just turn on in your company and hope for the best, right? Like we take many months with companies to like identify the kinds of boards they do. We try them, we see which kinds work, which kinds don't. We train the users, and that all takes a lot of time. In pretty much all cases, with almost any company we speak to, whether it's aerospace and defense or a large consumer or an automotive, there always exists a bulk of boards that are within our stated scope, right? In terms of the density, complexity, pin count, component count, you can almost always find that. The real question is just do we get to a good enough result that those designers are happy with, right? So that's how I know that we should be focused on reliability and constraints, right? Is if we were going to companies and describing that envelope and they said, we don't do any boards like that, then we'd have to push higher, right? But because people always give us an example that's within our stated scope, but just our ability to nail all of the design quality that they're looking for isn't there, that's why we've got to focus on that. So not to say we don't want to get to bigger and larger boards, we do, but in the name of focus, we've got to nail this first.
And it sounds like the right strategy to serve the wider audience. Everyone has a simple standard board that they need done quickly.
Deadlines creeping up like a bad horror movie? Don't let your project turn into nightmare on PCB Street. At SierraConnect, we'll get your boards fabricated faster than you can say impedance mismatch. High quality, lightning speed, check us out at protoexpress.com and meet your deadline.
What's a good design? So reliable, of course it has to function and turn on, but what else? Like if a designer is looking at the output of Quilter, on what other basis are they judging the output as good or bad that you didn't quite expect?
This is actually a really fun question to ask in sales calls because we always get different answers.
Okay.
Which is really cool. So I mean, you've named some of the big ones, right? Obviously, like I think somebody put it really well, saying quality is passing DFM on the first go. That's a good definition of quality, and I like that. Quality is the board works, passes qualification, and runs for 10 years, for sure. But I think some of the surprising ones are more about the life cycle of the board and what people have to do with it. Like we had a company that deals with operating like mining machinery. And these are like large, chunky boards that have to be field serviceable. And so for them, quality is, for one, can a technician who's not familiar with it read it and figure out like what's happening with it, right? So sort of like the readability of the circuit becomes a quality aspect. And for two is, can they field service it, right? Can they take off and replace a component? Can they grab the whole thing with gloves and not have to take their gloves off to put it back and forth? And like, that's not something we ever thought about until we spoke with that company. And so you get ideas like that as well that are surprising in terms of quality.
Absolutely. And then in terms of the manufacturability, I think the way I understood your process for 2025, there was Ben highly involved with our feedback. Have you thought about how you can use Quilter to help with that or put more of the manufacturing constraints in your tool?
Yeah, 100%.
Okay.
Like this is, at the end of the day, I mean, the ideal system here would be to like have all of the knowledge that you guys have and have it be available to the algorithm to know that that's what it has to satisfy, right? And that's not an easy problem by any means. But at the end of the day, it does at some point reduce into separations, distances, nearness, those sorts of things. And it's a matter of quantifying them. So, I mean, we certainly hope to work with companies like Sierra to understand that as well as we can. And as we make it easier to define more types of constraints, actually populating that with useful constraints is going to be the next step.
Yeah, exactly. I mean, building out an awareness of, like, I don't even know any single human who's been able to document very effectively more than about 50% of all the considerations that go into each board design for good manufacturing, say, or low-cost manufacturing. Things like via aspect ratio are, you know, issues that people know when you mention it. And so it's a bit of a task gathering a comprehensive set of all the possible constraints that might exist, but that it's important that we start climbing that mountain and climbing it as fast and hard as we can.
Yeah, it's hard. Every design is unique, and a capability page is very one-sided. It's not capturing the whole.
It's kind of extreme, really.
Yeah. So, yeah, it's even with all the constraints out there, constraints in the EDA tools, we still get designs with a bunch of issues every time. But we would love it if we were to get a design with 0 issues. Yeah, passing DFM the first time. Yeah. That would be amazing. I mean, we would love that.
I mean, honestly, I know for a fact the designers would love that too. Right?
Of course. There's so much back and forth right now.
Yeah. And it doesn't serve anyone, right?
It's just waste.
It's just hard. But it's hard, right? As a designer, when you don't sit next to the factory, you don't look at how the machines run, you don't see the ones that failed and that they caused low yield. Like, over 10, 20, 30 years of a career, you build that up. But then how do you pass that on to somebody out of year 1 or year 2, right? And I think that, at the end of the day, we have to just write them down. Like, we have to be able to compute whether or not we've met all these designs or not over time. And once we get to the point where we can, then algorithms have a hope of just meeting them all and passing on the first try. But until we can write them all down in such a way that the computer can actually just verify them and check them with high reliability, there's always going to be a human in the loop. I mean, I think maybe one thing, this is less of a point, but like with Speedrun in particular, for the interested reader, like we went to great lengths to document everything and put it on our blogs. So for those who want to see like the input files, the output files, the changes been made, the verification tests of this whole functioning, maybe we can link the blog in the description.
Of course.
But it's all there.
Yeah, no, it's very exciting.
I don't want to do too much of a shameless plug. But I intend to bring up the last board live if anyone wants to join. I haven't picked a date. Oh, no, we have a date. Sometime in March, early March. I don't think we've broadcast it quite yet, but I will be in my home lab bringing up the last of the 10 boards, the 10th board or board pair live. And it would be good to gather a crowd to watch. And it might be fun for them if smoke does finally come out of one of them, but I'm not anticipating that. All the others have been rock solid so far. So
nice.
You say that now. No
but
No
but
pressure.
the point is, while I'm doing that, people will want to ask me questions about it. I'd love to answer them as best I can about my involvement in this process as the double E on it. So
Nice. That's great. No, I think that's a great plug. I'm sure you'll get lots of viewers for that, lots of audience. I guess one question I want to ask both of you, everything's changed in a year, I would say, in the great AI race. What do you see as, changed the most for you from what you thought in 2025 to what you're thinking about in 2026 or even beyond?
It's an interesting question. I mean, I think that so much of the focus and time in AI right now is spent on effectively language models, right? It's spent on legal tech and code assistance and note summary takers and chat support. And it's remarkable, right? I mean, there was an article that came out this morning from Anthropic that they were able to have an agent or a set of agents create literally an entire C compiler that worked, and enough to compile the Linux kernel in about a week's worth of time. I mean, it's remarkable, right? That's unbelievable. But that is because all of this attention and pressure is going into language models, right? When you look more at like physical AI, like robotics, what we're doing, this kind of analog in the chip design space, and so on and so forth, like there's progress and there's pace, but it pales in comparison compared to what's happening in LLMs and so on and so forth. So I think that the things that we can learn now is less about like, Opus 4.6 comes out and it dominates Opus 4.5 or whatever is happening for code agents, and more about what are the paradigms of how people are working with AI where AI is already very advanced. And we're learning from that because that's what we are trying to build, right? Like, what is the interaction model? What does the human want to control? What is the best paradigm to give the human control? And even this blog article that I'm referencing about building the compiler, like the most interesting part of it wasn't that they asked Claude to go build a compiler and it worked. It was everything they had to do to make that possible, right? They put together 16 agents that were working together. They had to solve problems around how do you make sure that two separate agents don't tackle the same problem. They had to make sure that the output was actually good. And frankly, they had to rely on an existing human-built compiler to serve as a reference check against the AI-generated compiler, right? So a little bit of bootstrapping there. But all the techniques of like how to keep that context, how to make sure the agents collaborate, and so on and so forth are super interesting. And like specifically also how the human was involved in that process. So I'd say that's probably the biggest thing that we're learning from the general AI wave is like in places where the models are getting really good, what does that actually mean? And how do like jobs and human interactions change as a result of it?
That's great. That's a good one. Are you guys working on R&D in physical models, or you're using what exists, open source stuff out there?
Yeah, so we try not to do science. And what I mean by that is that, like, it's a company, it's applied research, right? So if I could take, a model off the shelf and say, please do a layout and have it do a good job, I would love to, but I can't. So for example, like the transformer model is a famous architecture in the large language model space because it's very suitable for sequences and it works quite well, obviously. However, there exist variants of the transformer that work equally well for image problems or geometry problems or graph problems even, and that's something we can make use of. So we didn't have to invent some new architecture completely, but we couldn't take a pre-trained one off the shelf and just ask it to do the thing. We had to take basically the architecture, but then set up the whole process of how to train it, pick the right kind of pieces of models to glue together into what makes sense for a circuit board. So I would very sharply call that like applied research, where your purpose isn't to discover some new fundamental breakthrough, it's to use the existing working pieces and apply them to a new application.
So you think building a circuit board is more akin to real world models than, let's say, LLM?
Yeah, I certainly think so. I mean, on a few different aspects, right? I mean, for one, building a circuit board is a kind of 2D, 3D problem, right? So already you're dealing with spatial problems, whereas language is kind of sequences, right? The next thing is that languages are graded by similarity to humans, right? Like large language models are excellent at making humans believe that a human might have said what was said, right? But they're not necessarily excellent at being true or being physically accurate, right? There's plenty of famous examples of LLMs like having no idea of like what physical reality is, right? And that's getting better over time, but it's not a core feature of those models. Quilter models have to ultimately respond to physics checks, right? The classic physics simulations. So yes, that is closer to what we might describe as kind of physical AI. But it is still a step away from something like a self-driving car, where your direct data is like camera data, it's throttle inputs, it's brake inputs, and stuff like that. We are sort of like a little bit more digital in that we are training against the simulation, not an interaction with the real world totally. And we rely on the fact that like the simulation and the geometry we've computed represents the real world.
Got it. Okay, as a devil's advocate, why Quilter and not Cadence? Why would Cadence not get to a good end result faster than Quilter?
Yeah, I mean, I think it's a good question. I mean, certainly, and again, it's not like I know exactly what Cadence is up to and how they're working on it, but I think from the marketing content I see from them, I don't see as much of a focus on the physics. And I think that's really, really, really fundamental, right?
You have an answer.
Yeah, and the only other thing I'll add is
Okay, go ahead.
the only other thing I'll add is like beyond the approach, there's the classic innovator's dilemma, right? Where Cadence is very likely to want to, for example, preserve the per seat model of the software, right? Cadence is also probably going to want to limit the users of their AI to users of Cadence. And so now they don't have access to the Altium crowd, they don't have access to the Siemens crowd, they don't have access to the KiCad crowd. And I mean, switching CADs, that's a whole other giant problem. So I would say that, right? Like, I mean, for one is the approach of physics. For two, it's the innovator's dilemma of a large company.
Yeah. Yeah, that second point was actually right in line with what I was going to say, maybe in different words, is that the whole ECAD industry has this momentum, or inertia is a better word, that's very hard to change direction with. It's like a massive flywheel that's spinning, and you try to tilt it, you know, like the gyroscope effect, because there's all of that with user base, user expectations, disrupting. You can't disrupt your 60,000 paying customers to get what may not turn out to be more than 10,000 new customers who are able to vibe code boards, let's say, just to use a stupid term, but it behooves us and the industry to do something completely fresh. For that reason, they just, and that's not an indictment on those tools. They're very powerful, and they have a lot of wonderful capabilities. They're very effective in the hands of people who've spent the time learning them. But this is also why we're very focused on solving this layout problem using physics, because that's how we get that time back. Yeah.
Yeah, I mean, I'll add one thing to that, which is that, like, if we approach a customer and work with them and for whatever reason fall short, the answer is never, oh, we're going to go use your competitor. The answer is always, we're going to go back to the status quo and let a human do it. And at the end of the day, what that tells me is that none of us have solved it yet. Right? And so when we at Quilter are working on the problem, we are not spending time thinking about, you know, what's Cadence doing or anybody else. We're thinking about the real competition, which is the status quo, right? And that's where we focus our time. So, you know, maybe there's better answers to why Cadence or why not Cadence, but really what I'm asking myself is why the classic way versus this way?
Yeah, it's always good to ask the right questions.
Yeah.
So that's a good question. Okay, I think I've asked what I needed to. The last time, Ben, you were on Trace Talks, I think I asked you a pie-in-the-sky question about AI, and you wanted AI to fold your laundry and a couple of other things. And that's what everyone's working on now, and it's coming to fruition. Do you have any other pie-in-the-sky asks or wants for AI?
I still have really the same ones. Like, I want it to offload the minutia, so I can have a clear mind to focus on things that really matter to me. And I don't think anyone else who's human would really disagree with that. I want more time to play guitar and have family time and certain things like that. I want time and freedom to explore new technology and research things myself, or generate content that's meaningful to other people. You know, like this podcast that's helpful, and you know, we're all on that search for meaning, right, in life, and sometimes it just feels like all the stupid details are in the way of that, and that's really where agentic AI should be helping us, and that's why it's such a hot topic right now, because it feels like we can grab it, but it's still only the expert users who've stayed with it up to this point who can really put it, like leverage it that deeply. And there's still a lot of danger involved. So,
Very true words.
yeah.
Good. Thanks for that insight. Cool. Well, I enjoyed the podcast. I loved you guys explaining your amazing project, and I look forward to what you have to accomplish in 2026.
Thank you.
Thank you.
Thank you for having
absolutely.
us.
Of course.